It says suppose you need 50 pounds of two commodities. We'll call them A and B. We don't know. Like a cheaper and a more expensive one. One's $1.25 a pound, one's $1.60 a pound. Verify first that the total cost would be this. Well, it's $1.25 times the first guy and $1.60 times whatever's left over from the 50 pounds. Yeah, check. I mean, I don't know how. I mean, I don't know really how you would verify that other than just to verify that's what it is, but whatever. Find the inverse. Well, switch X and Y, solve for Y. I would actually simplify the first guy first before I did an inverse, because that would be an ugly inverse to find if you don't simplify it. So distribute this little guy here. Oh, well, what are we doing? Nope. All right. It was not, it was writing way too thick. Distribute right here, right? And then combine your like terms. So you get like 1.25x plus, this is 80, minus 1.60x. So these combined are negative 0.35, I think. So y equals 80 minus 0.35x. So I'm just simplifying the first guy before I do an inverse, right? Because I don't want to do an inverse of that one. All right, so find the inverse. Well, how do I do that? Switch x and y. So we make it x equals 80 minus 0.35 y. Subtract 80, divide by negative 0.35. And they actually did it in decimal form, which is fine. So my inverse is going to be something like, when you take that negative 80 divided by negative 0.35, you get something like 228.6-ish. Minus, it's basically 1 divided by 0.35. You get negative 2.86x if you round it. So that's just finding the inverse and then making it decimal form instead of fraction form, because you're going to plug stuff back in. So this is my B. Find the inverse. Let's look at C. What happens with C? C says use the context to determine the domain of the inverse function. What does each variable represent? So find the inverse and what variables. We'll talk about that first. If initially the X represented my pounds of whatever I'm buying and my Y represented my cost, then in the inverse, those just flip-flop. So my X now represents my cost and my Y represents how many pounds of this first guy I bought, okay? So that's all. When you do an inverse, what they represent flip-flops as well, okay? So if my initial input was pounds and my output was cost, then it's going to flip-flop on my inverse. Now my input is cost and my output is pounds, okay? Make sense? All right. So use the context to determine the domain of the inverse. Basically, the domain of the inverse is going to be represented by the range of the initial problem. So like my domain here on the initial problem would be 0 to 50. That's how many pounds I can have, because they actually told me the two added together equals 50. So at most of this first guy could be 0 up to 50. Right? That would be the initial input. And the output would just be anything from this, once I got here, 80 minus 0 up to 80 minus the 50 times that guy. So those just flip-flop. So if you think about domain and range, just think about input, output. All right? And so if my input was anything from 0 to 50, that's now going to be my output. And if my input, my output then was 80 minus 0.35 times 0 and 80 minus 0.35 times 50, that's going to be my input now. So those just flip-flop too. Domain and range just flip-flop for inverses. That's all it's getting you to think about. All right, this is determine the number of pounds of the less expensive commodity, which is what I'm finding when I find X. That's what I did there. If the total cost is 73. So I'm just going to put my cost in here. Okay, that's now my input. I could go back and plug it in up here if I wanted to, but I've already got it solved for that. So I can just say 228.6 minus 2.86 times that 73. And I think you get I don't know if it rounds, but it's really close to 20 pounds. So if I had 20 pounds of this guy, then I should have 30 pounds of that guy. 50 minus the 20. In order to get a total cost of 73. All right, so we are moving from logs to natural exponents, which is base E. So your natural number E. All right, so we did derivatives of logarithms. And now we're going to look at derivatives and antiderivatives of your natural number E. Okay, the first thing they point out is the inverse function of a natural log. The inverse function of a natural log is called the natural exponential function. All right, if you recall, your natural log has a base of E. And so logs and exponential functions are inverses of each other. Just like log with a base 10, the inverse of that would be 10 to the x, okay? Inverses and bases are logs and bases are inverses of each other. That's all this is saying here. So if I were to take the natural log of a base E, they cancel each other out, just like addition and subtraction cancel each other out. If I add 3 and subtract 3, I'm where I started, right? That's the same kind of concept for natural logs and base E. So whether you're taking the natural log of a base E or base E to the natural log, they're going to cancel each other out all the time. So the first thing we're going to do is just that concept way back from pre-cal and algebra 2 when we did natural log equations like this. If I wanted to solve this guy, I could literally just do the natural log of both sides because I can get rid of my E that way. I can say the natural log of 7 equals the natural log of E to the x plus 1. And right here, these will cancel each other out. And I will just have x plus 1 on the other side. So I have these canceling. I have natural log of 7 equals x plus 1. So then I can solve by just subtracting a 1. Natural log of 7 minus 1 will equal x. You can put that into your calculator. It's approximately 0.946. Easy enough. Example 2, natural log I need to get rid of. Well, just do a base E for both sides. So on the left-hand side, I have e to the natural log of 2x minus 3. And on the right-hand side, I have e to the 5th. On the left, the e's and the natural logs cancel. I have 2x minus 3 equals e to the 5th. If I need to solve for x, add 3 divided by 2. X is going to be e to the 5th plus 3 divided by 2, which is approximately 75.707. All right, operations with exponential equations works the same, okay? If you multiply like bases, you add their exponents. If you divide like bases, you subtract their exponents. That is true of all bases, all right? Domain, e to the x, the domain goes from negative infinity to positive infinity. You can plug any power into that you want to. However, the range starts at 0 and goes to infinity because you cannot take your natural number 2.17, blah, 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 whatever he is, and raise him to a power to get him to 0. That won't work. Or to get him to negative. You're never going to get him to negative, right? So your range is going to be 0 to infinity. The function is continuous, increasing 1 to 1. The graph is concave up on its entire domain. And it shows you the limits here is what it's going from left to right. And then you can see a picture of the graph. Looks like this. All right, so it'll always stay above your x-axis. It's not going to go below it because of the domain. And then you can see how that works. All right. So let's talk about derivatives. Derivative of e to the x is e to the x. Pretty straightforward. If that x is anything but x, meaning it's like x squared, 2x plus 1, then you have to consider the derivative of that. Think of it like the chain rule, all right? So derivative of e to the x is just e to the x. If it is anything except x, you have to do e to that function times the derivative of that function, almost like you would do chain rule. That's where it comes from. So for example, derivative of e to the 2x minus 1. Well, that is going to be e to the 2x minus 1 times the derivative of 2x minus 1. Well, the derivative of 2x minus 1 is just 2. We wouldn't write it like this. That's hideous. We're going to write it like this, 2e to the 2x minus 1. That is the derivative there. E to the negative 3 over x. Well, that's e to the negative 3 over x times the derivative of negative 3 over x. You may want to write this out to the side, negative 3, x to the negative 1. That's how we would write negative 3 over x, right? Multiply by your exponent. Negative 1 times negative 3 is 3. Subtract 1 from it. We're taking derivatives, right? Negative 1 minus 1 is negative 2. That's my derivative. So we would say 3 over x squared. All right? Again, we wouldn't leave it like that. My numerator here would be 3e to the negative 3 over x. My denominator here would be x squared. But that would be my derivative. All right? So just like anything else, relative extreme happens at critical points. So we would find critical points here. I will point this out. This is a product. So you will need to use the product rule to do this one, okay? So the product rule would say the derivative of the first. Well, what's that? Well, just 1, right? Derivative of x is just 1. So I have the derivative of the first times the second the way it is. Well, that's just e to the x. Plus the first guy, that's just x. Derivative of the second guy, well, the derivative of e to the x is just e to the x, all right? If I'm going to look for critical numbers, I would set that guy equal to 0, right? That's where critical numbers happen. What can I factor out of this if I'm solving for this problem? Well, I can factor out an e to the x, right? So I can take an e to the x out. I'm left with 1 plus x equals 0. I set each factor equal to 0. E to the x equal to 0, and 1 plus x equals 0. E to the x is never 0. I just said that it starts at 0 and goes up, right? The range does, right? This right here is my derivative.
Yeah, I see. I was just trying to...
All right, so this guy will never equal 0. So this isn't going to give us a critical number, which means the only critical number we have happens at negative 1. All right, negative 1. So a relative extreme will happen at negative 1. I just plug that in to find out my y value if I need my x value. That's my x value at my critical number. So then I say, well, what happens at negative 1? Well, that's going to be negative 1 times e to the negative 1, or negative 1 over e. You can plug that in if you want to get the actual decimal value, or you don't have to, but that's where it happens. It happens at the point negative 1 over e. The number of medical doctors in thousands in the United States, represented by Y, obviously, from 1980 through 1997, can be modeled by this. And they've given us this function that is obviously an exponential function, right? Where t is 0, which represents 1980. At what rate are they changing in 1992? If they are looking for the rate in which they're changing, then you must find the derivative. That's rate of change, right? All right, if this were like a linear equation, rate of change is slow because it's steady. But an exponential equation, the rate of change depends on where you are because exponential functions shoot up versus linear, which has the same rate of change all the way across, right? So we have to find the derivative first, which means we just take this guy and multiply it by the derivative of that. So if I'm taking the derivative of my y, it's going to be my original 475, 520, e to the 0.0271t, that's big, times the derivative of that exponent. Well, the derivative is just my coefficient, 0.0271. All right, that's my derivative. They simplified it to, they multiplied these guys and got approximately 12,887 e to that decimal place there. And they want specifically in 1992. What am I going to plug in? Well, how many years away from 1980 is 1992? 12. So literally, to find out what the rate of change is, we're just going to take this guy and plug in a 12. You get that it was changing at approximately 17,839 doctors per year. Rate of change. All right. All right, integration is pretty straightforward. If the derivative of e to the x is e to the x, then the antiderivative of e to the x is e to the x. I mean, we have that plus c if it's not a definite integration. If the derivative of e to the u is e to the u times the derivative of e to the u, then the antiderivative is the same thing. We just have to make sure that our u is accounted for, like anytime we have u substitution. So let's look at these examples here. Example 7. Integrate the exponential function e to the 3x plus 1. Well, what is my u? We're going to set my u up as that exponent. My u is 3x plus 1. My du would then be 3dx. I don't have a 3 in there. So how do I do this all the time? Well, I multiply both sides by 1/3. 1/3 du would be dx. So I'm just going to say I could do 1/3 the integration of e to the u du. The antiderivative of e to the u is just e to the u. 1/3 e to the u plus c. Well, then I need to go back and plug this guy back in. So my answer is 1/3 e to the 3x plus 1 plus c. Okay. So you really just have to account for anything in that exponent where the derivative has not already been accounted for. Again, I can think of this just as in terms of u. I will say they rewrote it a little bit. So they rewrote it so that they could get a visual of what's happening. They took the 5 and the e to the negative x squared, and then they kind of grouped it with the x dx. So you could kind of see that x is going to be accounted for when I do my antiderivative right here. Now the 5 we're going to have to finagle, but the rest of it you can see. So if I make my u to be the negative x squared, then my du is going to be negative 2x dx. You can see the x dx is accounted for, right? The x dx is accounted for. But I need a 5, and I don't need a negative 2. To get that, I'm just going to multiply both sides by negative 5 halves. I promise this will work. If I multiply this by negative 5 halves and this by negative 5 halves, what happens over here? Well, I get positive 5x dx, which is exactly what I needed. So I'm going to replace this with that. So I'll say negative 5 halves. That's going to account for that 5x dx, e to the u du. E to the u is just e to the u when I take my antiderivative. So I have negative 5 halves, e to the, instead of u, I'm going to say what my u was, negative x squared plus c. All right, in this case, you may be tempted to to think that you need to replace something. But let's think about what you would be. You would be 1 over x, right? 1 over x. Well, what's the derivative of 1 over x? That's x to the negative 1. The derivative would be negative x to the negative 2, or negative 1 over x squared. That's just 1 over x squared, isn't it? X squared on the bottom. So really the only thing I'm missing is a negative. Everybody see that? So I can just say, well, that's going to be negative e to the 1 over x plus c. That's the only thing I was missing from there, was a negative 1, right? Look at this next one. If you can recognize it in your exponent is what I'm saying, just like we did before. If you can recognize it, you can go straight to it. This is obviously my u. What's the derivative of cosine? Negative sign. So the only thing I'm missing is a negative. This is accounted for in my u. So negative e to the cosine of x plus c. Like, there's not much work to be done there when it's accounted for, right? When you can see that it's accounted for in there. The only difference here is you're going to plug your numbers in at the end. I mean, that's all you have, right? So like, what am I have here that I need to account for? That negative 1, right? I'm missing a negative 1. So if I were to take the antiderivative here, it'd be negative e to the negative x. That's my antiderivative. I don't need a plus c. Why? Well, because I have these guys, 0 and 1. Just plug it in. Negative e to the negative 1 minus negative e to the 0. All right? Which ends up being just negative e to the negative 1 plus 1. But when you plug it in, you get approximately 0.632. You're actually going to get answers here, okay? So the only difference between these and the ones we've been doing is when you get your antiderivative, plug it in. Just don't think of e as a variable. That's what starts happening in your brain, is you start thinking of it as a variable, and it's not a variable, it's a number. So when you go plug these in, you're plugging them into x, and you're just taking e to a power, okay?